The air that we live in and breathe is a gas. Due to the relatively open molecular spacing of a gas compared to liquids or solids, gases are highly compressible. Compressed air contains and can transport energy, and it is therefore a versatile medium frequently used in control applications and as a source of mechanical power in manufacturing and industrial processes. The use of compressed air in this way is referred to as pneumatics. This course will cover the following topics: gas fundamentals, including the relationship between pressure, temperature, and volume, and gauge versus absolute pressure, benefits and uses of compressed air, compressor design and operation, and air quality considerations and processes, including cooling, drying, and filtering. There are a number of benefits offered by compressed air. Compared with other energy distribution systems, such as hydraulics or electrical systems, compressed air systems are economical. The base medium, air, is free. The systems have relatively low maintenance cost, fewer moving parts, and, unlike hydraulic systems, require no return lines. Pneumatics are also relatively safe. Most importantly, there is no risk of electrical shock. The pressures in pneumatic systems are 10 to 20 times less than those in hydraulic systems. Compressed air is versatile and has a wide range of applications, from use in fine-tuned instrumentation to heavy-duty hoists. Pneumatic systems can provide high torque, fast actuation, and high motor speeds. Finally, compressed air systems are reliable. Compressed air systems include an air storage element which offers some surge capacity even in case of power failures. The versatility of pneumatics lends itself to a broad range of applications. These can be broken into two general categories of use: instrument and service. Instrument applications make use of compressed air's ability to perform delicate and controlled operations at lower pressures, smaller volumes, and relatively low rates of consumption. Instrument air uses include pneumatic controllers and pneumatic valve actuators. Service applications usually involve the use of compressed air at increased pressures, larger volumes, and higher flow rates to perform work. Service air uses include pneumatic motors, pneumatic hand tools, and blow-down air hoses. Due primarily to the small size of the equipment used in instrument applications, the quality of instrument air needs to be higher than the air used for service applications. Many processes and machines are controlled by components which use compressed air. This means that maintaining both the quality and quantity of this seemingly lowly utility is critical to operation of your site. A loss of air pressure or contamination of the air system has the same dire consequences as the loss of electric power. When compressing air for a pneumatic system, it is important to understand the fundamental relationships of the physical properties of a gas. The combined gas law describes that for a given mass of air, as the volume of air is reduced through compression, its pressure and temperature increase in directly proportional increments. The pressure and temperature increases represent the energy which goes into compressing the air. In the United States, volume, pressure, and temperature are typically measured in terms of cubic feet, pounds per square inch, and degrees Fahrenheit, respectively. Pressure is the force exerted by a gas against the inner surface of the container or vessel in which it is held. Pressure is usually expressed as a force per unit area, or pounds per square inch, or PSI. There are two ways of expressing a given pressure: gauge pressure and absolute pressure. These two methods differ in how they account for atmospheric pressure. Although it may seem that there is no pressure in the air that surrounds us, In scientific terms, there actually is. As a result of being beneath the 18-mile thick layer of air which surrounds the Earth, the atmospheric pressure at sea level is 14.7 psi greater than the absolute zero pressure of deep space. In most situations, we really only care how much pressure exists in excess of atmospheric pressure. This is referred to as gauge pressure. Gauge pressure uses atmospheric pressure as its zero point. The second method of expressing pressure uses the complete absence of pressure, such as in deep space, as its zero or reference point. An absolute pressure includes the pressure of the atmosphere in the reading. Thus, a gauge on a tank which indicates 150 psi is said to have a pressure of 150 psi G, or pounds per square inch gauge. If the tank is at sea level, where atmospheric pressure is 14.7 psi, the absolute pressure inside the tank is 150 plus 14.7, or 164.7 psia, or pounds per square inch absolute. All of the numbers used in this course will be gauge pressures unless otherwise noted. The heart of any pneumatic system is its compressor. A compressor is a device that increases the pressure of a gas by reducing its volume through the addition of mechanical energy. This also increases the temperature of the gas. A compressor is similar to a pump. Both increase the pressure on a fluid, liquid or gas, to transport the fluid through a pipe. Gases are compressible, and so a compressor reduces the volume of a gas. Liquids are relatively incompressible, and so the main action of a pump is to transport liquids. The requirements of a given system determine the optimum type and capacity of compressor. Compressors are driven by either internal combustion, steam turbine, or electric induction motors. Their capacity is measured in cubic feet per minute, or CFM, at a given discharge pressure. The three most common types of air compressors include reciprocating, rotary screw, and centrifugal units. Reciprocating compressors are positive displacement machines. They use a piston mechanism driven by a crankshaft which cycles into and out of a stationary cylinder, compressing and displacing a volume of air with each stroke. Reciprocating compressors can be stationary or portable, single or multi-staged, and can be driven by electric motors or internal combustion engines. This technology is currently used primarily for smaller mobile compressors. Older reciprocating compressors up to 1,000 horsepower can still be found in industrial applications, but their numbers are declining as they are replaced by more cost-effective technologies. Rotary screw compressors are also positive displacement machines. These compressors employ two rotating, interleaved helical screws which capture air in a pocket between them. The space in which the air is trapped becomes smaller as it moves down the axis of the screw. The compressed air is discharged from the opposite end of the intake. Rotating screw compressors can be used in applications ranging from 3 horsepower to over 500 horsepower. They are commonly used by roadside repair crews to power air tools and are also used for automobile engine superchargers. Centrifugal compressors are dynamic compressors. In this type of compressor, air enters at the center of an enclosed high-speed vaned disc or impeller. The rotation of the impeller adds energy and accelerates the air to the outside of the case. As the gas exits the case, the kinetic energy of the gas is converted into pressure. Centrifugal compressors are well suited for continuous, high-capacity, stationary service in industry. Centrifugal compressors can range from 100 horsepower to thousands of horsepower. With multiple staging, they can achieve output pressures in excess of 10,000 psi. The quality of the air within a pneumatic system is dictated by the end user's tolerance to heat, moisture, and other potential contaminants. For example, the finely tuned moving parts of a pneumatic loop controller are significantly more sensitive to high temperatures, condensation, and dust than a 5-ton pneumatic hoist. In order to prevent corrosion, costly repairs, and downtime, specific procedures and equipment are employed to control heat and moisture to predetermined and measurable tolerances while preventing the introduction of contaminants. An unfortunate side effect of compressing air is that it becomes heated. The sources of heat are compression and mechanical friction. As the combined gas law illustrates, air gets hotter as it is compressed. The air is also heated as the result of friction between moving parts inside the compressor. Heat generated by mechanical friction is controlled through proper lubrication and cooling systems integrated into the compressor. Lube oil coolers remove heat before it is transferred to the air. Heat in the air, which is the direct result of compression, is removed by sending the compressed air through water-cooled heat exchangers. Because cooler air retains less water vapor, cooling the air also helps manage its moisture level. A given volume of air at a given temperature can hold a fixed amount of water vapor. Dew point is one measure of the amount of water present in a volume of air. Dew point is the temperature at which the air becomes completely saturated with water vapor and liquid water starts to form and drop out of the air, or condense. As ambient air is compressed, its moisture concentration and dew point increase. Air compressed to 100 psi occupies about 1/8 of its original volume, but it still contains all of the original water vapor. If this air was sent directly out into the site and was then returned to the ambient temperature, a considerable amount of liquid water would drop out. Cooling the compressed air in a heat exchanger immediately after it exits the compressor gives the water a single point to condense before going into the site. Large pneumatic systems which run continuously may also cycle compressed air through a regenerative drying system which uses heat and a desiccant material to remove water vapor prior to storage. Desiccant dryers are used to further treat the air and bring its dew point down low enough to reach instrument air standards. Desiccant dryers typically have 2 vessels of desiccant. At any given time, one vessel is in the process, absorbing water from the compressed air, while the other is in a regeneration cycle, where water is removed from the desiccant. The 3 major types of pneumatic system contamination are airborne solid particles, oil vapor, and moisture. Airborne contaminants such as dust, microorganisms, and oil vapor from ambient air are prevented from entering the system by industrial filters at the intake port of the compressor and are managed throughout the system by purification filters at critical points. Oil vapor can originate from ambient air, but it most commonly comes from the compressor itself. Since almost all air compressors use oil in the compression stage for sealing, lubrication, and cooling, lubricating oil may migrate into the compressed air system as a liquid or as an aerosol. This oil, plus the water vapor in the air, can create an acidic mixture, potentially damaging the compressed air storage and distribution system, production equipment, and ultimately the final product. Oil vapor contamination is prevented primarily with proper maintenance of seals and specialized absorption filters. Cooling and drying, after the compressor, removes the majority of moisture in the compressed air. Additional specialized filters may be employed throughout the distribution system to capture any remaining water vapor in order to protect sensitive equipment.